Dear students, I promised you that I will be making a video on this particular topic, abnormal molar mass from chapter solutions before your board exam. So here is the video. Let's start with the topic quickly. Why abnormal molar mass? First of all, what is the concept basically? So, abnormal molar mass is related to colligative properties, first of all, their calculations. And you know that what are colligative properties? The properties which depend upon the number of solute particles. Now, suppose I have potassium chloride as a solute in a particular solution. And potassium chloride will be dissociating in water, in aqueous medium, to give me potassium ions and chloride ions. So it is very easy to understand that potassium chloride will give me more number of ions. So the number of solute particles I added will be giving me double the quantity. That means one potassium chloride particle will give me 2 ions. So 2 moles of particles in the solution, it means the number of particles are increasing here, hence it is going to affect the colligative properties calculations. Colligative properties like relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, osmotic pressure, all those properties. Similarly, let us take another example. Suppose you have 2 molecules of ethanoic acid, which is also called acetic acid, and it dimerizes. Here is the dimer. You can see that because of this hydrogen bonding, 2 molecules, they are joining with each other. And this happens specifically in the solvents of low dielectric constant. Like it will dimerize in benzene, not in water. In water, it's going to dissociate to acetate ion and H plus ion because water has high dielectric constant. Okay, that is one point. Now here, suppose I start with 2 molecules of ethanoic acid. What am I getting? I am getting 1 molecule of the dimer. So because of dimerization, or I can say because of association of molecules, the number of solute particles are decreasing. Again, it is going to affect the colligative properties calculations. So that is why we are discussing about abnormal molar mass. If I take any such example where association or dissociation is taking place of the solute particles in the given solvent, and then I calculate colligative property, or suppose in a particular question delta TF is given to me and association or dissociation is taking place. Using that delta TF, for example, if I calculate molar mass of the solute, it is going to be different from what is expected because of the dissociation or association, right? Okay, so let's understand it in more detail. If all the molecules of KCl that I start with, they dissociate in the solution, expecting 100% dissociation because it's a strong electrolyte, then the value of change in boiling temperature, change in freezing temperature of the solution will be more than the expected value that it should be. Delta TB is equal to Kb into molality. Right. This value, if it is twice than expected, and molar mass, if I calculated on the basis of this value, that molar mass will be half of the expected value. Why so? Because here it is molality, number of moles of solute divided by kilograms of solvent. So number of moles of solute means here if I write given mass of the solute divided by molar mass. So molar mass will be in denominator here. This delta TB will be inversely proportional to the molar mass of the solute. So if delta TB or delta TF is coming out to be twice, the molar mass has to be half of the expected value. Similarly, another case, if I take ethanoic acid where the dimerization was taking place, association was taking place in benzene as a solvent, there the value of delta TB, delta TF is going to be half of the normal value that it should be. Why? Because association is taking place and the molar mass is going to be twice of the expected value. Again, the delta TB value is inversely proportional to molar mass of the solute. So that is why this happens. So it is very clear that molar mass will be either lower or higher than the expected value or the normal value. That's why we are calling it abnormal molar mass. For instance, for a particular question, I give you the value of delta TB and I ask you to calculate the molar mass of ethanoic acid. And their association is taking place. So whatever mass you are getting after calculation will not be the normal molar mass of ethanoic acid that we calculate using this formula. It will be almost double of that. To make it more clear, let's look at the questions which will be discussed after this particular slide, because here I want to tell you that what is the solution to this problem, that everywhere we are coming across abnormal molar mass. So how to solve the problem? For that, Hoff, he introduced a factor I which is called Hoff factor, or it is called the correction factor. By definition, if you go by the definition and the formula, it will be normal molar mass divided by abnormal molar mass. Suppose the normal molar mass of a particular solute is X, but the association is taking place and the molar mass is coming out to be 2X. That means this cancels. I will be half, right? The mass is coming out to be double and I already have a correction factor 1 by 2. So that double value 2 into the expected value will be taken care by this 1 by 2. So that is why we are calling it a correction factor, right? Then it can also be written as observed colligative property divided by calculated colligative property. This I'll be explaining in the upcoming numerical. Or it can also be expressed as total number of moles of particles after association or dissociation, or the number of particles before association or dissociation. For example, if you have KCl dissociating as K plus and Cl minus. Now in the beginning, at time 0, when this reaction did not take place, this dissociation, it was 1 mole and they were 0 moles. After the dissociation, it will be 0, because we are expecting that 100% dissociation will take place and you will get 1 mole of this and 1 mole of this. Now put the values in this formula. Number of moles of particles after association or dissociation. So this is after dissociation, 1 plus 1, 2. So it will be 2 divided by number of moles of particles before. Before there was only this one, they were 0. So 2 by 1 is 2. Here the value of I will be 2. This is how we use this correction factor. And now how to use this for correcting the formulas. Let's move on to that. The abnormal molar mass is experimentally determined molar mass. Experimentally, we'll measure that for a particular quantity of solute. Then we are putting it to make a solution in the limited quantity of solvent. Then what is the change in boiling point, delta TB? Using that, if I calculate the mass and association or dissociation is taking place, then the value will be abnormal molar mass. So this is experimentally found. And the calculated value of mass is the value that we expect, that if I have CH3 COOH, I have 2 carbons, so 12 into 2, 24, plus 4 hydrogens, 4, plus 2 oxygen, so 16 into 2, 32. So this will be 28 and 32, 60 grams. This is what I expect, right? As per the formula. So this will be the normal value. But when I do the calculation, experimentally found will be the abnormal if there is association or dissociation. Right? Okay. Now, in case of association, the value of I is less than unity, less than 1. As I gave you the example of KCl, the value of I was coming out to be 2. So here, the value is greater than unity, that is greater than 1 if dissociation is taking place because number of particles are increasing. For ionic compounds, you can take like MgCl2. MgCl2 is going to give you Mg2 plus and 2 chloride ions. So whatever number of ions are formed, 1 here and 2 here the value of I will be 3. Those compounds which are not completely ionic, those which have less ionic character, there the value may be in fraction, may not be exactly 3, 2, 1. It may be 2 point something, like for calcium chloride, it is around 2.47. So that will be provided to you if you have to solve a numerical. Now the inclusion of Ventoff factor, which has modified the equations of colligative properties as follows. The first is relative lowering of vapor pressure. So on the right hand side, you multiply it by the correction factor I. If the mass was coming out to be double, then the value of I will be roughly 1 by 2. So it will cancel that 2 into the mass with the 2 which is in the denominator here. So on the right hand side, if I take I everywhere in the formula, that is the modified form of the different formulas for these colligative properties calculations. Let's have a look at this table, which is from your book NCERT again. As I told you, if it is ionic compound like NaCl, 1 Na plus ion, 1 Cl minus 2, so I value is 2. Because after dissociation it will be 2 ions, and before dissociation it was just 1 particle. So 2 by 1 is 2 straight away. Same way for KCl, already discussed, 2. MgSO4, 1 Mg2 plus ion, 1 sulfate ion, 2. For K2SO4, 2 potassium ions, 1 sulfate ion, so 2 plus 1 is 3. I value is 3. Sometimes you can expect such questions, 1 markers, MCQs, very short answer type questions, that for this particular compound, what is the value of I? And they'll be asking you those which have very clearly stating that complete dissociation is taking place. So that will be always a whole number, right? Now here you will notice one more thing, that they have given you different molalities. For example, take NaCl. The value of I is increasing when the solution is becoming more dilute. Because if the solvent is more, then the dissociation of solute takes place to maximum extent. And you will see here it is reaching almost 2, 1.97, very close to 2. And when we expect complete dissociation, that means very dilute solution. So it will be written as exactly 2. Let's start with the numerical, a very interesting one. Many of my students, they keep telling me every year that these two numericals which are in the end of the chapter, they are confusing. So I am purposely taking them up here. 2 gram, this is the salt example from NCERT. 2 grams of benzoic acid dissolved in 25 grams of the solvent benzene, and the depression in freezing point, that is delta TF, is 1.62 Kelvin. The value is given. And the molar depression constant, that is Kf, that is 4.9 Kelvin kilogram per mole. Now question is, what is the percentage association? So they are telling you that here the dimerization is taking place. Association is mentioned here. So first of all, the technique is you find out the Ventoff factor I. do the calculation. How will you do that? You will make use of the formula delta TF is equal to KF into molality. Molality is weight of the solute divided by molar mass of the solute divided by the weight of solvent in kilograms. If it is in grams, then you need this 1000. Otherwise, if it is already in kilograms, then you don't need that 1000. Be very clear. So this is the expression for molality. Simple. What they have explained in NCERT, that using this formula, you calculate the molar mass of the solute. All these values are given to you. This is provided, this is provided. Weight of solute is 2 grams that you are taking. Weight of solvent is 25 grams. Everything is given. सब कुछ दिया हुआ है. So you will just put the values and you will find out the molar mass. Why this is required? I have the formula of benzoic acid. So I know the mass of carbon, hydrogen, oxygen. I can calculate. But that will be the calculated value. Here it will be the experimentally found value. So that we can make use of the formula for I. Now, I hope you are able to understand it. Let me tell you again quickly. Except this, all other values are given. So you calculate this using all other values. This will be the molar mass. Or you could have done it this way also. Take the modified formula. Delta TF is equal to I into KF into molality. Put the value of delta TF, KF, molality may be, you know this molar mass from the formula of benzoic acid, 122 grams aayega. Put the value, you can calculate I. The value calculated from here and the value calculated by taking the ratio of this molar mass and the molar mass by the formula. These two I values are going to be same. So that is up to you. See, they have written I values here. I value here. That is 122 normal molar mass, that from the formula, and abnormal molar mass that we got from the calculation here. And never ever round it off. Exactly up to 2 decimal places or 3 decimal places, do the calculation. This is the only tough part here, nothing else. And you will notice one more expression for I. One more expression for I. How has it come? It's written in the question that association is taking place. So if you have C6H5COH, 2 moles, it is associating to give you a dimer. That we write like this. Suppose in the beginning you started with 1 mole of this, so this was 0. After that, what happened? Out of this 1, suppose X quantity is consumed in making the dimer. So it remains 1 minus X, and 2 moles are giving 1 mole of the dimer. So if X is used, how much of this remains? X by 2. Should I write it separately? Okay. Let me do that to make it more clear to you. C6H5, 2 moles of benzoic acid, dimerizing. This cannot be 100% association. So there will be some percentage association which we are trying to calculate. So this is how we write the dimer. 2 moles of monomer giving 1 mole of dimer. Clear? At time 0 initially, when the association did not take place, suppose I started with 1 mole of this was 0. After some time, if X quantity of this is used in converting it to the dimer, so 2 moles are giving 1 mole of dimer. So if I use X, it will be giving me half of that, X by 2. Now put the expression of I, the values in the expression of I. Number of particles after association. So that is going to be 1 minus X plus X by 2. These are the total number of particles or moles after association. And before association, it was 1 plus 0, that is 1. That's why They have written it like this: 1 minus x plus x by 2, because it was divided by 1. So that doesn't matter if I don't write 1 here. This I have got from the expression which I just explained to you. And it becomes 1 minus x plus x by 2 would be minus x by 2. So 1 minus x by 2, this is also I. And this is also the value of I. Equate them and calculate x. X is coming out to be 0.992. X is degree of association in this particular case. In equilibrium chapter class 11th, we used to write alpha. So it is the same alpha. Here they are using x. And percentage would be, if I convert this to percent, that how much it's going to be for 100. So it is going to be 99.2% association. That is the solution of the first solved example, which was creating problem for so many students. I hope if you go slow by pausing the video wherever you want, or you can go back and watch the particular slide again, I hope it is going to help you. Okay, the next solved example from NCERT is in front of you. It has 0.6 ml of acetic acid having density this much, so volume and density given, dissolved in 1 liter of water. The depression and freezing point is given, and the value of Kf will also be given to you. That will be 1.86 as given here for water, kilogram per mole. This value will be provided. Kb, Kf values are always provided. So you have volume, you have density. Using this, you can calculate the mass of the solute by multiplying them. Divided by the molar mass of acetic acid, 60 grams, you will get the number of moles of solute. Why do we need this? Why do we need number of moles here? Because in the question you have to calculate dissociation constant of an acid. So Ka is C alpha square by 1 minus alpha, where this alpha is degree of dissociation or association in a particular question, that we are taking as x here. And C, concentration, is represented as N here, number of moles. So that's why we are taking it up like that. So first of all, number of moles are calculated and it is converted to molality, not molarity. It has to be small m, molality. So that will be number of moles of solute calculated here, divided by the kilograms of solvent, which is 1 liter water. That means 1 kg water. So it is coming out to be this value only, 0.0106 moles per kg. Now how to calculate Vent-Off factor I? That is the first part. Delta TF is calculated using the formula delta TF is equal to Kf into molality. All the values are given to you. Still they are not taking this delta TF, they are calculating it. Once you calculate, then you can take the ratio. This was given, this is calculated, you can see there is difference. And when they find out the ratio, that is 1.041, this is the value of Vent-Off factor I. There is one more way of doing it. You take the modified formula, delta TF is I into Kf into molality. Then use the given value 0.0205, use Kf, molality, everything, calculate I. So both the ways you will get the same answer. So that is up to you how you want to calculate. So I jab calculate ho gaya, then you have to make use of this equation of dissociation. Initially it was n moles in the beginning and they were 0, 0. After that, जैसे हम इक्विलिब्रियम में लिखते थे C minus C alpha करके, same way n minus nx. So taking this C common, 1 minus alpha, so taking n common, 1 minus x. If you make use of x quantity, if the degree of dissociation is basically x, so if C alpha is used, then you get C alpha here. Same way, if nx is used here, you will be getting nx. Why? Because 1 mole is giving 1 mole of this and 1 mole of this. Now we know how to write the expression for I. That is total number of moles here after dissociation. This plus this plus this. that is coming out to be n minus nx plus nx plus nx. So this cancels and you are left with n plus nx only. N plus nx only here, divided by the number of moles before association or dissociation in this case. So before that it was n plus 0, that is n. So that n is here now. When you put the values here, this cancels. So 1 plus x I have got as the value of I, and earlier by taking this ratio here, we got the value of I as 1.041. So we equate the two. So x comes out to be this. Now once I know the value of x, I can calculate how much is the value of acetic acid by putting x here. How much is H plus value and how much is the concentration, the value of acetate ions, just by putting n value and x values here. I have all the values. Now I can make use of the formula, that dissociation constant, if I have to calculate, that will be simply concentration of products divided by concentration of reactant. So put the values here and you will get your answer simply like this. So this is easy way of calculation. Seems difficult, but believe me, it is not. If you do it twice, you may not get this question in the exam exactly, but whatever based on this concept will be given, you will be able to explain it nicely. Then one more thing, if this is given as change in some temperature, delta T F is given here, never ever do this mistake that add 273 to 0.0205 because you want to convert it to Kelvin. Whether it is in Kelvin or in degrees Celsius, the change in temperature will remain the same. So delta TF is 0.0205 degrees Celsius or 0.0205 Kelvin, same rahega. Why? It is like, if you have 1 degree Celsius in the beginning, it changes to 20 degrees Celsius. How much is the change? Delta T, 20 minus 1, that is 19 degree, right? If you convert it to Kelvin, it becomes 273 plus 1 Kelvin, changes to 20, so 273 plus 20 Kelvin. The difference is again 19. That's why I'm saying this. So I hope I'm able to explain this question to you. So you have calculated degree of dissociation and then you have calculated dissociation constant also. Here, concentration, you can see. So I can write this as C square alpha square. In this case, in this question, it is written as n square x square. Those values only. Divided by C square alpha square divided by C 1 minus alpha. So this square cancels. C alpha square by 1 minus alpha. Same way here, n 1 minus x. So this cancels. You get nx square divided by 1 minus x. Same thing. If this is confusing you, don't worry. Simply use this expression, this concentration into this concentration of the products divided by the concentration of reactant. Put the values here. Same answer you are going to get. Now two simple questions from NCERT exercise quickly where I is incorporated. Determine the amount of calcium chloride. The I value is specified here because it is not that ionic like the potassium chloride or NaCl types. That's why the value cannot be a whole number, but this is a good value. Still the dissociation is quite good value. I is 2.47. It is dissolved in 2.5 liters of water. So the osmotic pressure becomes this at this temperature. Everything is given. Pi is equal to CRT is the formula. So correction factor is incorporated. That is given to you in the question. Put the value. Put the value of pi that is given to you. R value you already know, 0.0821 liters atmosphere per Kelvin per mole. Convert this to Kelvin, 300 Kelvin. So everything is simple application of the formula. You'll get the answer easily here, quickly here. The only thing is you have to incorporate this I here. In some questions, they will not give you the value of I, where you have such solutes. It is clear that it will dissociate to give me 2 K plus ions and 1 sulfate ion. So the value of I will be the number of ions here, because it's written that assume complete dissociation. So I am assuming complete dissociation. I am getting 3. Value of I as 3. Again, make use of the modified formula. Put the value of I here, 3. Simply multiply all the other values which are given by putting them at their correct place in the formula. You will get your answer. Here the value of I is not given. And if you forget about I, your answer will be totally different from what it should be, because whatever you are getting here, suppose you are getting n as your answer, but your answer should be 3 into n, because this 3 is very important. So don't miss this value. If it is written clearly that assume complete dissociation or association, then please do make use of that. So that is the end of this presentation. I hope I have helped you in understanding a difficult concept. All the best for your board exams. Do well. Thank you.